Hello, today we are going to be looking at the second derivative test. Now, yesterday we talked about concavity, and concavity just talks about the second derivative. So if the second derivative from yesterday was less than 0, we said a function is concave down. And if we said the second derivative of a function is positive, we said the function is concave up. Well, today we're going to continue on this lesson right here and just to talk about how concavity can help us determine if we have a relative maximum or minimum. And it's super easy to do, and we will come back to that in just a few moments. But in the meantime, let's kind of review a little bit of our derivative test. Our derivative test from yesterday and the day before. So we're given the graph of a derivative. Right here, remember this is my slope graph, and we're asked on what function is what intervals is the function increasing or decreasing. So we know that this is our first derivative test. That's from a couple days ago. And so since this is the graph of our derivative, we are looking at anything above the x-axis being a positive slope, anything below the x-axis being a negative slope. And of course, anything on the x-axis is where our slope is 0, and of course those are our critical numbers. So if we want to find out where a function is increasing, we first have to find our critical numbers. That is, where is the derivative 0 or d and e. And on the graph here, it's pretty easy to see. Remember, we're looking for the slope is 0, so we're looking at the x-axis itself. And we're going to get -3, 1, and 5. Writing our sign chart, on top is the derivative, and on bottom is the function itself. And we don't have any domain restrictions, so we're just going to list out our critical numbers, -3, 1, and 5. And then we look at their slopes. Well, we're looking at the slope, anything before -3. Be very careful. It looks negative, but remember, this is the graph of my derivative. And that simply says anything above, we're saying we have a positive slope. So since we are above, we have a positive slope. So the function before -3 is going up. Between -3 and 1, we are below the x-axis. So it's a negative slope. It's going down. Anything between 1 and 5, again, is above the x-axis. So it's positive. The function's going up. And anything after 5 is below. So it's a negative. So the function's going down. And now we're going to find out where the function is increasing and decreasing. So we're looking for the slope is, of course, positive. So we know that this function is increasing on the domain -infinity to -3 or 1 to 5, and that is because the first derivative is positive. Our function is decreasing on the domain -3 to 1, where the slope is negative, going down, or from 5 to infinity, and that is because our derivative is less than 0. And you might also remember we can actually find relative maximums and minimums as well from our first derivative test. Notice we don't ever get anything from our graph, we're going to get it from our sign chart. A relative maximum, this is where the slope goes from positive to negative, and a minimum says the slope has to go from a negative to a positive. So if I'm looking for relative maximum here, I'm looking anywhere where the slope goes up and then down. And of course that is occurring at -3 and 5. We can't really see it from the graph. That's why the sign charts are so important for us. As a matter of fact, sign charts are so good, most AP readers just look at your sign chart and they'll pretty much know if you got the answer right or wrong. So we have a maximum at x equals -3 and 5, and that is because the derivative goes from positive to negative. A relative minimum, same idea, but now the slope goes down and then it goes up, and that occurs at 1. So we have x equals 1, and that is because the derivative goes from negative to positive, and there's our relative max and mins. Alright, so let's take a look at the next one. Now the next one is the graph of a second derivative. Remember, this is now concavity. That's our second derivative from yesterday. So concavity of a graph says if the function's opening up or opening down. Is it going to hold water like a cup, or is it going to spill water like a frown? So we want to find out where the function is concave up. So we need to find out where the second derivative is positive. So they give us the graph of the second derivative. Remember, this is my second derivative. And just like the graph of slope up here, if we're above, we have a positive slope. If we're below, we have a negative slope. Well, on our concavity graph, we have a positive second derivative. In other words, above the x-axis, the function is concave up. Below the x-axis, we're saying that we are concave down, and that is where the second derivative is negative. And in the middle, that is where our second derivative is 0. We'll talk about that also. Now, so in order to find the intervals, we have to find the critical numbers for the second derivative. But you may recall, we call them something different. They are called possible points of inflection. What this means, a point of inflection, you might recall from yesterday, is where the concavity changes signs. If we're starting concave down and going to concave up, where do they meet? That's what we're looking for. Concave down, concave up. Where do they meet at? And it's really hard to tell looking at this graph, so we're not going to use a graph, we're going to use a sign chart again. Getting the possible points of inflection, these are where the second derivative is 0 or d and e. And we can look at the graph, that's going to be our x-axis again. So we get -2 and 3. Writing out your sign chart, the second derivative, how does it make my function look? -2 and 3. And again, we're just going to look if the function is really just above or below. Same thing as with the slope. We're looking for above if it's positive, below if it's negative. It's even true, like remember back in the early days of when you learned how to graph polynomial functions, where you did polynomial inequalities in pre-cal? Plus 3, let's make the x minus 4. You want to find out whether that's greater than or equal to 0. You would do a sign chart, and you would do the same thing. -3, 3, and 4. And you would do a sign chart. Is the function above or the function's below? And you would do like plus or minus, and of course this one's not too bad. If I pick x equals, let's say, -4, this is going to become negative, negative, negative. So this is negative, so this is below the x-axis. And this is negative, this would be positive, negative, positive. And you were looking for where we're above, so you would look at the domains. We did the same thing back in pre-cal. We're just doing it a little bit further. We're not just looking at the values, we're now looking at the slope and the concavity. So if I'm looking for where the function is concave up, I'm looking for where we're above the x-axis. If they give me the value of the second derivative. If they give you the derivative, we'll talk about that at another time. So if it's above, before -2, so this is positive, we are saying the function's concave up. Between -2 and 3, also we're above, positive, so it's concave up. And between 3 and infinity, then we're below, now we're negative, concave down. So where is this concave up? On negative infinity to -2. But you got to stop at -2 because that's a possible point of inflection, and it stops there. It's actually equal to 0 there, so it's not up or down. And then from 2 to 3, and that is because the second derivative is positive there. And that's where we're concave up. State the points of inflection. Now you might recall a point of inflection is where concavity changes. So at 2, the concavity doesn't change. It's still positive and positive. But at 3, we go from positive to negative. So we have a POI at x equals 3, and the simple reason is because the second derivative at 3 changes signs. And we saw that yesterday when we talked about concavity. All right, recall. Now this little bit of recall here to kind of help us get an idea about how useful the second derivative is for us. Recall the sign of the second derivative at a particular x value determines if the function is concave up or concave down. we can use that to determine critical numbers, our relative max and relative minimums. So let's take a look. Let's imagine we have a function opening down like this. Here we have a relative maximum. Well, at the relative maximum, let's talk about the derivatives. I know at the very top here, the derivative is 0. Well, what can we say about the second derivative? Well, because it's concave down, the second derivative is less than 0. So one way we can define a relative maximum is if we have a critical number and it's opening down. That's basically it right there. It's opening down. So we have a critical. So if I have something opening down, well, where's my critical number? At the very top. It's a maximum value. Now be careful. Sometimes people think, oh, it's less than, so it's a minimum. Be careful. This tells me it opens down. Downward facing parabola, my favorite yoga position. What if then we have a relative minimum? Well, let's talk about that. Let's say we have a parabola opening up or function opening up. What can we say about the derivative here? Same thing. The derivative is still 0. Our second derivative now is greater than 0. This opens up. And if we think of something opening up, let me rewrite that. That looks terrible. Opens up. There we go. If we have a function opening up, at the very bottom, we have a critical number, and that's going to be a minimum in this case. So one way we can define a minimum is if we have a critical number and the second derivative is positive. So let's use that. Determine if the vertex of this parabola is a relative maximum or minimum. We should know this. This is a downward facing parabola, so we should have a maximum. But let's see if our second derivative test works. First, got to find the critical number. So y prime would be negative 2x plus 4. Find the critical number. We're going to set that equal to 0. We get x equals 2. So there's my critical number. At this point, we have either a minimum or a maximum. Well, to do this, we're now just going to check the concavity. If we take the second derivative, we get negative 2. And if you notice, this never changes. And negative 2 is less than 0. Therefore, this is saying that the function y is opening down. And therefore, we can say the vertex f of x has a relative maximum at x equals 2, and that is because the second derivative is less than 0. And that's what we write. Now, notice what I should do is also this, and this is very helpful for people. Once you know that this opens down, don't say it opens down. Y opens down. Draw it so you can see that that's a max. I would encourage you all to just draw it out or use your hands. Concave down, concave up. It's very helpful. All right, I'll see you guys in part 2.